Okay, before I start taking questions, I just want to point out where we are in the class. In the meantime, if you have questions, you can be jotting them down. So this is week 4 that we're about to finish. We have a quest. You were allowed to use calculators in this one, so I'll go grab some if people need to borrow them. Scientific calculators. Okay, so next week is the last week of new material for the class. And the packet for next week is over on the side table. Make sure you grab it before you leave if you haven't already. It's the last week of new material for the class, and it's the last quest. So just to remind you, you've had 5 quests. You'll have had 5 quests. One gets dropped. Another one can get replaced with your final exam grade if it helps you. And week 6, the last week of the course, I had not planned to do any kind of quest or assessment. It was just going to be review. But I thought it would be fun to give you a group practice final on Thursday. So I'll write a special practice final. You'll take it in groups. The whole class can be a group if you want. You can all discuss it. And then that practice final can count as a 6th quest if it helps you. So it can raise your quest average. The week after. Next week is next week is the last week of new material. We'll have a typical, regular quest that week. And then the following week, our review week, on Thursday, you'll take a group practice final. So it will give you a sort of a flavor of what the final will look like and a little boost to your quest average. No. No, it's just because I'm nice. Okay, so that will be used as a 6th quest grade if it helps you. It should help you because I'm hoping that everyone will work together and there'll be a class full of A's. And then the last week, we only have class on Tuesday. That's the day of the final exam. The solutions to that practice final, I will put up right after you leave class, or that evening maybe, so that if there's any stragglers, so you can look at the solutions if there was anything you weren't sure of. Okay, so it doesn't matter if you use either the law of cosines or the law of sines to figure out measurements in a triangle. No, use whichever one works. Okay. In general, if you have side angle side or side side side, you use the law of cosines. This is just sort of like what you would have figured that out. I think it's the only thing you can use, right? If you have angle, angle, and then a side, or side, angle, no, side, side, angle, side, side, angle, you use the law of sines. Do people know what I mean when I write those things? Side angle side means you have 2 sides in an angle, right? And the angle is between the 2 sides that you know, right? So if this were like 5 and 5 and 80 degrees, something like that. Yeah, that's SSA. I wrote it there. Very carefully. So side angle side means you have 2 sides and the angle between them. Side 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 obviously means you have the 3 sides, no angles. Angle angle side means 2 angles and then a side. So this could be like 80, 30, and then you have a side, which could be 10. So angle angle side. And side side angle means you have 2 sides in an angle, but the angle is not between the 2 sides. So you could have like 10, 10, and then an angle of, I don't know, 40 or something. Does that make sense? Okay. Okay, so multiplying a vector by a scalar just lengthens or shortens the vector. So if you wanted to draw 2v, this vector in the plane is v. If I want to draw 2v, it would just double the length. Right, so we would just draw it again. So it's over 2, up 3, over 2. So this would be my new vector, 2v. And then half v would just make it half. So it would look like that. And negative v would like flip it to go the opposite direction of what it's going in now. So it'll be the same length, over 2, down 3, but opposite direction. Okay, given the displacement vectors 4, 5, and 3, 2 in the figure below, draw the vector v minus 2w with the starting point at the origin. Okay, so it looks like I'm missing a picture here. Okay, so we have v is 4, 5, so that's over 4, up 5, that's v. And w is 3, 2. So v minus 2w. So first, I'm going to think of that as v plus negative 2w, because I know how to add vectors. It's easier than subtracting. And so negative 2w means take w and put it in the opposite direction, right, that we just talked about, and double its length. So instead of going over 3, up 2, it's going to go left 3, down 2, and then we're going to do that twice, left 3, down 2. So this vector in pink is negative 2w. Does that make sense? Okay, so now I want to add v and negative 2w. So the way you add two vectors is the head to tail method, where you pick one up. So this guy, you pick it up and you put it with v, putting its tail to the head of v, like that. So I can move mine around. You have to kind of imagine it on your paper. So put that there, and then this point where it ends up, that's the resulting vector. That's the difference. That's the sum of v plus negative 2w. So in green, that's the answer, and it looks like that is negative 2, 1. So that's how you do it graphically. Algebraically, we could just say, okay, 4, 5 plus negative 2 times 3, 2. Well, that would be 4, 5 plus negative 6, negative 4. If you distribute that negative 2, and then combine like terms, right? Add the x's. 4 plus negative 6 is negative 2. 5 plus negative 4 is 1. Yeah. Yeah, so you can do this algebraically by just do negative 2 times w and then add them together. Add the x's, add the y's. Or graphically by using the head to tail method. Okay, so if I give you a polar form, a point r, are we talking of a complex number or just coordinates? I don't know who asked this. Okay, so let's do a complex number. Let's say we have a complex number z. We tend to call complex numbers z because we've already used x and y for real numbers. So we call complex numbers z. And let's do 3 plus 4i. So a complex number can be plotted in something we call the complex plane. So if I wanted to plot a complex number, it has two parts, a real part and an imaginary part. So we have a real axis and an imaginary axis. Right, so real numbers, if you just wanted to graph the number 10, you'd put it on a number line, right? If you want to visualize graphically a complex number, we have to show both of its parts. It's got a real part and an imaginary part, so we have to use a plane. Okay, so the number 3 plus 4i in the complex plane is just the point 3, 4, right, in the complex plane. So I would plot the point 3, 4. 3 is my real part, 4 is my imaginary part. There's my point z, my complex number 3 plus 4i. Okay, so I want to convert the point 3, 4 to complex form. It needs an r and a theta. Okay, so I need to know r and I need to know theta. And I know x is 3 and y is 4. So I've got this right triangle. And I need to convert to r and theta instead of x and y. So I could say, well, 3 squared plus 4 squared should give me r squared. So r should be, yeah, which is what? Right, so what's r? 5. Thank you. Yeah, it's a 3, 4, 5 right triangle. So we've got the r. I just need the theta. So I'd like to know what theta is, and I could say, okay, well, I know the tangent of theta is 4/3, right? Opposite over adjacent. So I could just take the arctangent of theta, or the inverse tangent of theta, of 4/3 to get theta. So that'd be approximately no, the angle in a 3, 4, 5 isn't 45. Arctangent of 4/3 is 0.927 radians. Just to address what you just said. Yes, but it makes it to make a 90-degree angle, not to make a 45. So if you have a right triangle that has a 45-degree angle, that means the other angle has to be 45 degrees also to make them add up to 180. And if two angles of the triangle are the same size, that means that it's an isosceles triangle, and these two sides would have to be the same length. So it's impossible to have a 3, 4, 5 that has 45-degree angles. So the 3, 4, 5 rule used in construction is to verify that you have a right angle right there. Yep. Okay, so we have 3 plus 4i. And now I want to write this in r e to the I theta form. So I know r is 5, and I know theta is 0.927. So one thing that you learned in your notes this week was that if you have a complex number, it can always be written like this, right, where you have an a and a b, real part, complex part, or it can be written like this, r e to the I theta. This was not verified for you or anything, so you just have to say, like, okay. And someday, someone will verify this for you, I promise. Okay, so any complex number can be written as a plus bi or r e to the I theta. It's two different forms of the exact same thing. So r e to the I theta, I know r and I know theta, so this is going to be 5e to the 0.927 I. Okay, so there is my polar form of the complex number. Okay, so I just went Cartesian to polar, right? I started out with a Cartesian 3 plus 4i, Cartesian 0.34. We converted it to a polar point 5, 0.927, and then put that complex number in polar form. All right, so I'm going to go backwards. If I start with the complex number in polar form, 5e to the 0.927i, and I want to convert it to polar. I'm sorry, convert it back to standard. I would say, okay, 0.927, that's somewhere in the first quadrant. This is 0.927. I know my radius is 5. It's a right angle. I'd like to know x and y. So I could say, well, the tangent, that's not going to help. I can use the cosine of 0.927. That would be x over 5, adjacent over hypotenuse. And then I could solve for x by multiplying both sides by 5. 5 cosine 0.927, which is, should give me 3. Let's see. I'm going to take this number that has lots of decimal places, 0.927, blah, 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 and store it as the letter A so that I don't have to write out all those decimal places. And I don't have to round, so my answer will be more accurate. All right, so I'm going to do 5 times the cosine of that number I stored as A, and I get 3. So x is 3. Y is going to be 5 times the sine of 0.927, which should give me 4. 5 times the sine of that number I stored as A, and I get 4. So I've converted back to Cartesian coordinates 3 and 4. So I know I should be able to write this as 3 plus 4i. In general, you don't have to draw that picture every time. I like to because it just reminds me why the formula is true. But r e to the I theta, the way we graphed it there, just means you have a hypotenuse of r and an angle of theta. That will always come out to r times the cosine of theta plus I times the sine of theta. Right? Your x will always be r cosine theta. Your y will always be r sine theta. And so if you factor out the r, and then you throw the I on the sine part, because that's the y coordinate, the imaginary part. So this is a general formula that you probably saw in the notes this week. Euler's formula, yeah. Yeah. That is, yeah, I think that is Euler's formula. Oh, e to the I pi. Yep. Yep. Because e to the r theta, like I just said, sorry, r e to the I theta. If r e to the I theta is r times cosine theta plus I sine theta, then if r is 1, right, then if I want to do e to the I pi, r is just a 1, so that's going to be cosine pi plus I sine pi. Cosine pi is -1, sine of pi is 0, so you just get -1. E to the I pi. 3 of the most famous and difficult to understand numbers in mathematics combined this way. E to the I pi gives you one of the simplest numbers in mathematics, -1. It is. Vectors. So a vector is really just a point in the plane with an arrow that points at it. So so here's a vector at the point 3, 1. It's just a point, but with an arrow that points at it. Okay. So, I mean, it's kind of weird for me to, like, why would I introduce this thing that just means a point, but an arrow that points at it? Like, so it has to do with when you take physics, you will explain forces a lot as a vector, and the so a vector has a magnitude, which is like its strength, which you denote in a picture by the length of the arrow, and a direction, right? So all forces in nature have a strength, how strong is the force, and a direction, which way is it pushing or pulling. So we just represent those kinds of forces mathematically with a vector. We represent the strength of it as a length and the direction with an arrow that points in a certain direction. So two forces can work together or against each other or sort of together, right? So like if Brittany and I were playing tug of war, you know, the stronger force is going to move the rope in their direction. So we'd be working against each other. Or let's say we were trying to pull a boat or a car or something. Brittany and I could both pull at the same time, and we would add our forces together. So my force would be represented by a vector. Brittany's would be represented by a different vector, and we could add them together. We could subtract them and make them cancel each other out somewhat. Or if we're both, I don't know why we would do this, but if there's a car and Brittany has a rope and I have a rope and I'm kind of pulling like at a 45-degree angle this way and Brittany's pulling at a 45-degree this way, the car is going to move forward, but we're not adding our forces directly together. So you can combine vectors in all different ways, and vectors just represent forces. Yeah, we can make it pretty complicated. So this is just a quick intro section of how to represent forces as vectors, how to combine them mathematically. So you can add them directly together, you could subtract them, etc. Yes? I don't think we covered that. That I and J represent unit vectors. I is the unit vector in the x direction. So starting at 0, 0 and pointing at 1, 0, that's the vector I. And you put a little arrow over a vector to say that that's a vector, not a variable. And then J is the unit vector in the vertical direction. So J is in green there. So the vector I drew over here, you can take any vector and write it as components. This is just 3 times the unit vector in the x direction plus the unit vector in the I direction, in the J direction. Yes. So V written as components is 3I plus 1J. And yes, I could also, instead, I could just give the length of the vector, which I'd have to find by using the Pythagorean theorem, right? This is 3 and 1. The length of the vector V, which you denote with like sort of double absolute value bars, which you could also just think of as the radius or the hypotenuse. That would be square root of 10. And then you could give an angle. We don't usually have a notation for that. We just we just describe the force as having a length and a direction. Like this example says, Ian is swimming across a river that's flowing due south. The current is strong. He's angling himself in a direction 20 degrees north of due east. The current is pushing him due south. And then it gives the vector at which he can swim in still water, right? 0.7 meters per second. And the speed of the current is 0.3 meters per second. So you have two vectors, the strength of two vectors, a 0.7 and a 0.3. Those we'd call those velocity vectors. And there's two. There's one for Ian, and there's one for the river, right? And the river would be, the river is flowing due south. So the river's vector, if I started at 0, 0, its direction is due south and at 0.3 meters per second. So let's call this 0.3. So there's the vector that represents the force of the river. And then Ian has his own force, right? And he is swimming 20 degrees north of due east. So due east is the positive x-axis. 20 degrees north of that. And the strength of his vector, I drew it longer than the strength of than the river vector because Ian's swimming stronger at 0.7 is the length. Okay, so that's a diagram of the situation. And then the resultant velocity vector, you add two vectors together by doing head to tail, right? So I would take the river's vector, put its tail to the head of Ian's vector, 0.3, right? So my resultant vector would be that guy in purple. Your angle for south, you could call that -90 or 270, either one. So that would be my picture. And then we have to use the law of cosines to find the length and direction of the resultant. So let's see, I know we're running out of time here. This is, yeah, so I knew the angle between the pink and the green here is 20 degrees. If that blue hit the green, it would be 90. So 90 and 20 is 110, so that's got to be a 70-degree angle. So now I have a triangle with side, angle, side. I could use the law of cosines to get the third side, to get the length. And then you could use the law of cosines or the law of sines to get the angle. In general, we treat that where a is a constant is going to be the amplitude of that trig function. Usually it's a constant, so it just goes up and down the same amount. I can put a function there instead of a number, like e to the x. Right, replace the a with a function instead of just a number. And that means that this function is going to look like sine, but its amplitude varies. Its amplitude is going to be e to the x. So instead of putting, 5 and -5 and varying between that, I would graph e to the x and negative e to the x. Right, so there's e to the x, there's negative e to the x, and then I would draw the sine function where those guys are my amplitudes. Rough sketch. Yeah, that's very rough, yeah. Oh, that would be interesting. So y equals cosine x sine x, for example. So cosine would be the amplitude for sine. I don't really want to do that. So cosine looks like this, right? And then the sine function would be, I don't even know how to do this. Don't worry about it. Yeah.